So, hello. Let's start our seminar. So, we are pleased to have a seminar inviting Sourav Roychowdhury from Chennai. So, he will talk about Non-Abelian T-dual of Klebanov-Tseytlin background and Penrose limits. Yeah, please start.
So first, I would like to thank the APCTP organizers, especially Kangun, to give me the opportunity to talk here. It's my great pleasure to present my work with the pupil. So here is the title of my talk, the Non-Abelian T-dual of Klebanov-Tseytlin background and its Penrose limit. The work has been carried out with the collaboration of my advisor. His name is written here, Prashant Tripathi in IIT Madras in India. Okay, so first I'll talk about a kind of motivation and introduction of our work, followed by the technical details, and then I will enter the core part of our work, and finally I will conclude and give some ongoing directions. Okay, let's start. Okay, so why the plane wave background or the PP wave background is important and interesting in general relativity as well as the string theory picture. Okay, so first of all, the PP wave background that has two main features. One is it admits a null killing vector. The second one is it whatever scalar you can construct from the PP wave geometry, means the Riemann or any combination of any scalar like up to some derivative, whatever scalar you can construct from the PP wave background is identically vanishes. Now, as we know from the worldsheet formalism in the string theory, that all alpha prime correction are accompanied by the Riemann scalars or any of the scalar. So now, sorry? Yeah, okay, sorry. Yeah, so now as we know in the string theory picture, that all alpha prime correction is actually come together with the scalars, the Riemann scalars, and as I just told, for the PP wave background, all curvature or all scalar vanishes, so it provides the exact string background. So that's the main beauty as far as the string theory picture is concerned. So PP wave gives the exact string background. Now, if we consider the Polyakov actions, which is actually the sigma model actions for the string theory, and if you consider the sigma model actions for the PP wave background, it is exactly solvable. Means it is exactly solvable. Means it's just reduced to some it's just reduced to Klein-Gordon equation for massive scalar field as far as the bosonic sector of the full string theory is concerned. So it drastically becomes simple. Now, one can construct via the famous ADS-CFT correspondence, one can construct the interesting string state in the guest theory perspective. Now, there is in the ADS-CFT correspondence is very interesting in the PP wave scenario. Means if you consider the closed string modes, means if you consider the closed string in the PP wave background and if you quantize it, you will get some certain modes. And this modes is actually a one-to-one correspondence between certain operators in the dual guest theory. Means if you consider the PP wave and if you consider the closed string, means the closed string quantization in the PP wave, you will get some modes, and this modes is actually one-to-one correspondence between some certain operators, which these operators is actually some restricting operators in the dual guest theory, which is actually some delta minus J, where R symmetry charge minus the U1 charge in the global symmetry. So this work, actually the first work, this PP wave, this seminal works is actually carried out by these three people, the Bernstein, Maldacena, and Nastase in 2002, and they showed this operator, the certain set of operators, what I told here. This operator is actually named the BMN operators by their work. So now BMN introduced this work in 2002, and after that, there are now over the decades, after the BMN picture came, then over the decades, people have studied this PP wave, the BMN picture in type 2B compactifications for the higher supersymmetry. This is actually the work by the BMN, the most supersymmetric case, the ADS5S51. And then people actually did some follow-up work for the least supersymmetric case, which is the Klebanov-Tseytlin background, as well as the fractional brane background, and so on, so on. However, very recently, people have turned on interest to examine this PPOA BMN picture in, Okay.
No.
So, okay, sorry. Okay. So now, recently, people have turned on interest this BMN PPOA picture in the Tdual of those type 2B compactifications. Now, here Tdual means the abelian and the non-abelian. Okay. So now, in the famous work by Buscher in 1990, follow-up work by Hassan, we know that how to construct the abelian solutions means if your background admits some U1 isometry, then the work by Hassan, then the work by Buscher and Hassan, we can generate its Tdual solution. Here Tdual means the abelian Tdual solution, and we know this abelian Tduality is the exact symmetry in the string theory, and it is the all order of string. It is the symmetry of all order. Means there is no alpha prime issue. This is the symmetry of all order of alpha prime. So it is the exact symmetry. However, very recently, people have generalized this abelian, the work by the Buscher and Hassan for the abelian case. Now people have generalized the ideas for the non-abelian isometry. Means if your background admits some non-abelian isometry like SU2 or SU3, now one can generalize the idea of the abelian one can generate the new solution. This is actually the main theme of the non-abelian T-duality, and one can generate the non-abelian T-dual solution. But there are some certain issues are there. This is the non-abelian T-duality is actually is not a symmetry of the full string theory. So there are some alpha prime issue which are still people are trying to resolve, but so far there is no so much understanding how to resolve the all alpha prime order. There are some work about alpha prime cube. Anyway, so now so far understanding for the non-abelian T-duality is it is just a solution generating technique at the low energy excitation of the full string theory. Means if you just focus in your attention for the low energy excitations, means at the supergravity level. So this classically is actually a great solution generating technique. It is not a symmetry of the full string background. So that so it is so far understanding is just a solution generating technique, and it is actually generalization for the abelian T-duality what is well established. Okay. Now the obvious question one can ask, if it is not a solution generating technique, if it's not a symmetry of the full string background, then why we will care about the non-abelian T-duality? Well, the answer is it is although it is not a symmetry of the full string theory, however, it is a beautiful solution generating technique at the low energy excitations. So means one can consider some known type 2B compactifications like ADS5, S5 or Klebanov-Tseytlin background, and one can apply the non-abelian T-duality formalism and end up with new type 2A or type 2B solutions. This solution actually have new boundary dual CFT. Okay. Now recently, in 2018, the group of Swansea people actually started to investigate the PP wave and the BMN in this non-abelian T-dual solution, and they worked out for the ADS5 S5 case, followed by our previous work. We generalized their ideas in the non-abelian T-dual of Klebanov-Tseytlin background. Now in the present work or in present presentation, actually what we did, we considered the Klebanov-Tseytlin background, which admits some non-abelian isometry, and Swansea people have already worked out their non-abelian solution. And in the present work, we examined the BMN and the PPOA, BMN, all this for our non-abelian T-dual of Klebanov-Tseytlin background. Okay. This is.
Can I add something?
Yes, sure.
Yeah. So this non-abelian T-duality transformation preserves the asymptotic ADS structure, or
yes. Yeah. I will come.
Oh, yeah. Okay.
Yeah, I will actually talk about great detail, the technical details, all these things.
All right, thank you.
Yeah. Okay. So these were actually some kind of motivation and introduction of our work. So now these are the outline. So as I just told to Kangun, First, I will talk about the non-abelian T-duality, means the technical details, how one can construct the non-abelian solutions from the known one. Okay, now I will briefly mention the Penrose limit. After that, I will enter the core part of our work. This is the two section of our core part. First, I will talk about the type 2B compactifications, and then is the T and the Tdual geometry of it. And then I will investigate the Penrose limit in the Tdual background. And if time permits, then I will make some comment. Actually, dual field theory is not well established, but if time permits, I will make some comments on the dual field theory, and I will end up with my conclusion and future reactions. Okay, let's start. Okay. So, as I just mentioned, the non-abelian duality is actually the generalization of the abelian T-duality for the isometries where the isometric group is non-abelian, like SU2, SU3. Just as a quick recap, what we do for the abelian case, the work by Buscher, first we consider a sigma model actions on the background, which admits some U1 isometry, and we guess the isometry. Means first we introduce the gauge fields, and then we consider the sigma model actions, and then we integrate out the gauge field and gauge fix the group part. We'll end up the Tdual model. This was actually broad line of work by the Buscher. However, actually at very beginning, if you consider its abelian counterpart, non-abelian T-duality goes actually along the same line. So means here also we gauge a global isometry by first we consider a nonlinear sigma model actions, and we gauge a global isometry and integrate out the gauge fields and gauge fix the group part. So this was actually worked by Strifios and Thompson in 2010, and they consider some various background and how to gauge fix these issues are already involved their work. And okay, however, there are some certain differences from its abelian counterpart. Here, for the non-abelian case, here the gauge fields is actually group value. This is actually the gauge field. It is the group value, where TA is actually generators of the group up to some constant factor. Okay. Now, in order to express the symmetry in the background, we will take help from the Meinon-Cartan forms. So this is actually the Meinon-Cartan forms, and where Ti is actually the generator. This is the left invariant Meinon-Cartan forms, and Ti is actually the generators of the group up to some constant factor. So now, what the group dependence which we actually interested to dualize is encoded in the left invariant Meinon-Cartan forms. Sorry. Okay. Now the question is how to construct the Tdual geometry. So first consider a generic background. Generic background means it admits some non-abelian isometry. So first we decompose the background in the following fashion. This is actually the spectacular parts. It doesn't depend on the group part. And this one direction is actually depends on the group part. And this is actually that all dependence in the group part. So we actually take care about the last part. Anyway, so this same decomposition one can work out for the Klebanov field in a sector, and this is the decomposition. This is actually more or less same decomposition. So this is the decomposition of the Klebanov field for the NS sector. Now, okay. So now we have a dilaton, and dilaton. So I'm going to consider the most general case. So there is a dilaton, and dilaton is actually completely dependent on the spectacular directions. So now, in order to carry out the non-abelian solution, what we will do, first we will consider the wall sheet Lagrangian, and this is the wall sheet Lagrangian, where the Q is actually take over G and B, and similar decompose here also one can do for the spectacular parts, and is completely the group part. And this X mu is actually the fields on the wall sheet, because we know in the wall sheet formulations that that's the background, the background coordinates as the fields on the wall sheet. Okay, so now, in order to construct the non-abelian solution, first we'll gauge the isometry, means we'll introduce the co-derivatives followed by the gauge fields, and these are the okay. So first we will introduce the co-derivative, and this is the gauge field. Now there is okay, and in okay. So now we add a Lagrangian multiplier in the wall sheet Lagrangian in order to invoke the flat connections. However, now there are two paths. So now if you consider, sorry, is there any questions?
No, please
Okay.
go ahead.
Yeah, so okay. So now if there is a two paths, so if you consider the equation of motion for the Lagrangian multiplier, effectively means this curvature vanishes and you will end up with the original. So you will go back to the original Lagrangian. However, here, in order to construct the Tdual solution, what we will do, we will talk about the equation of motions of the gauge fields. And here you can see there is no, these gauge fields are non-dynamical because there is no kinetic term. So in order to construct the Tdual solution, we will calculate the equation of motion for the gauge field and put back into the actions. And gauge fields the group part because there is some certain degree to maintain the degrees of freedom. So we'll gauge fix the group part and we will end up the Tdual model. So
if we consider some abelian subgroup of that, then it reaches the conventional Boucher transformation or setup of Bouchers.
Yeah.
Okay.
So yeah. So this. Yeah. So all this actually, it's same thing actually along the same line. Yeah.
All right. Right.
So here, So here only the group field, the gauge fields are SU2 value, and that's actually all. Okay. So now, as I just was saying, that here also along the same line, we gauge fix the group part, and here we just these are the equation of motions of the gauge fields, and we will put back this gauge field equation of motion of the gauge field in the original actions, means Q. We will end up with a dual model. Here Mij is defined by this expression. Here Fij is actually the structure constants for the corresponding Lie algebra. So we'll put back these gauge field equations in the original model and we'll end up with the dual Lagrangian. So this is actually the dual wall-sheet Lagrangian. And in the dual sector, you can see this VIs, which we introduce actually the Lagrangian multiplier. This behave actually the coordinates in the dual sector. Now from the dual Lagrangian, one can read off the dual Q's and dual E's. These are given by these expressions. And from dual Q's, the symmetric part of the dual Q's give you the metric in the T-dual sector, and the antisymmetric combination of Q give you the NS Klebanov field in the dual sector, and VI's means the Lagrangian behaves as a T-dual coordinate in the dual sector. Yeah. So this is like the exact expressions of the spectacular directions as well as in the group direction for the dual sector. Okay. And I just mentioned the symmetric part of the Q hat will give you the metric and along with the hat, and the antisymmetric part give you the B2, means the NS2 form, and the Lagrangian multiplier behaves as the coordinates. Okay. And this is end up the NS sector for the T-dual sector. So this is the background for this is the metric of the T-dual background, and this is the 2 form. And there is a dilaton. One can push the dilaton by changing the. One can change the dilaton by change the dilaton to absorb the Fedde-Popov determinant. So this is actually the T-dual dilaton. Okay. So this complete the NS sector, means how to construct the NS sector in T-dual solution. Now we have to talk about the RS sector. However, you can see from the wall-sheet Lagrangian that if you consider the left-right derivatives, which is expression which we wrote as Li plus and Li minus, in T-dual sector from, sorry, if you consider the Lagrangian for the T-dual case, it can be shown that these two derivatives, the left one and the right one, is actually changed differently. You can see from the expression. Means in T-dual sector, this Li plus and Li minus is actually generate two sets of Wehrbeins. However, these two sets of Wehrbeins are describing the same geometry, means the same T-dual sector. So they are not independent. They actually are, so they are not independent. So they must be related by a Lorentz transformation given by this expression where Aij is a Lorentz transformation. So however it looks, we have a two Wehrbeins. So at the end of the day, they are just actually the same, they are describing the same geometry. Okay. So now in order to construct, this plays an important role to construct the RS sector in T-dual theory. Yes, any question? Okay. So, okay. So now this Lorentz transformation is actually induce an actions on the spinner, because we know the order in RR sector, we express the flux in terms of one-to-one correspondence with the Clifford algebras, means with the gamma matrices. Now, this Lorentz transformation is actually have actions on a gamma matrices followed by this expression where this omega is actually the spinorial representation of the Lorentz matrix. Now, for most general case, we know for the type 2b compactifications, we have the odd fluxes, and in type 2a, we have even fluxes. Now, in order to construct the fluxes in Tdual sector, first we construct a bispinner, which is given by this in type 2b, and this similar expression in the type 2a, and this flux transform according to this principle. So from there, we can invert the flux by consider the spinorial representation of the gammas, and from then one can read out the Tdual fluxes accordingly. Okay. Okay, so is there any question so far? Hello?
Yeah, please go ahead.
Okay, sorry. Okay. So, yeah, so Kangun, now I am talking about the example, what you asked actually.
Yeah, great.
Yeah, anyway, yeah. So, okay. So far I have talked the technical details in the sense from the, how one can construct the Tdual solution from the known ones supergravity solution, and I talked separately for the NSNS sector as well as the RS sector. So now I am just a brief example. Just consider the famous ADS5 S5 background, which are actually in a sector we have just a metric, which can be written as a ADS5 parts together with a S5 part. And in our sector, we know in our sector we have only F5, which is actually effectively the volume of the S5. Now we will focus on the S5 part. So okay, so S5 metric can be written as a S2 over a fibration over a S3. Okay. So now this S3 actually supports some SU2 isometry. So in order to dualize, in order to construct the dual solution, we only bother about this part. So now, as I just mentioned, first we will write the S3 metric in terms of the minor current forms, which is effectively some delta ij li lj. And from there, you can construct the corresponding mij with its inverse. And that's why, and people have already constructed the dual solutions of the ADS5 S5 case. The Swansea people have worked out the dual solution, and this is the dual solution. So ADS5, okay, so the ADS5 part will remain as ADS5 because this ADS5 and S2 part is behaved as a spectacular part. However, this S3, there's an interesting thing in the non-abelian T-dualities, there is a non-compact direction. So you start with some S5, which is all directions are compact. However, after the dualization, one non-compact direction has opened up, and there is a fibration over the remaining S2. Okay, and this metric is actually singularity at theta equal to pi by 2, because this actually the fiber shrinks to 0 at theta equal to pi by 2, as well as your background dilaton blows up at theta equal to pi by 2. So there is some singularity theta equal to pi by 2. This plays actually important roles to quantize if you consider the full string background, because there is some issues about the non-compact direction and how to actually make compact the direction. This plays, the singularity plays an important role, which I'm not going in details for the time constraint, and this is actually open up some other directions. Okay, so now this background actually supported by,
hello?
Yes?
Yes, I have a small question.
Yeah.
So Sourav, why do I need to visualize the S5 as a S2 fibration over S3?
Okay, so actually, yeah. So you can have any deformation you can construct. So actually, we are actually inherited to we need to the S3 part to actually to express the SU2 isometry.
That's right, I understand. So yeah. This story will not go ahead with if I write generically an S5 metric, or are you saying that?
Sure. So yeah, sure. So maybe, yeah, so in metric will be its metric will look differently, locally diffeomorphic actually.
Oh, locally diffeomorphic.
Yeah.
Okay, thank you.
Yeah, sure. Okay. Yeah, so now this background is actually, so this is about Tdual background where the Swansea group of people worked out. And interestingly, this background is actually not n equal to 2 supersymmetric, rather n equal to 4 supersymmetric. Now I should mention just 1-2 points here. So obviously question you people will ask that how the supersymmetry breaks, because okay, naively, if your dualized direction depend on the killing direction for original solution, this actually break the supersymmetry. Okay, so for this case is actually ADS5 case is important example along this line, because we started with some n equal to 4 supersymmetric solutions, but at the end of the day, after non-abelian T-dualization, we will end up some n equal to 2 type 2b, n equal to 2 type 2a compactifications. Okay. So Kangun, are you now fine?
Okay, thank you. Is there any different viewpoint of this new background?
So that okay, so this for the debrain setup, actually, yeah. So if you when you consider the field theory perspective, that plays important role, because if you place the debrain, actually what I am trying to lead, this theta equal to pi by 2 plays an important role, how to place the debrains. And these are actually these are the intersecting brains. So it's like r equal to 1 pi by 2, we'll one debrain will loop up into the 2, and then next pi by 2 will go to 4. So this kind of debrain, intersection debrains are pictures in the, if you consider the field theory perspective.
I see.
And so it's very actually I am thankful to you that you have raised this issue. So in field theory perspective, actually for the non-abelian case, or only that much is understandable so far, how the debrain behaves. Right. Nothing more actually. I'll come actually. Yeah, I'll come.
Thank you.
Yeah. Okay. So now actually I have finished some certain part, because so far I am talk about how to construct the Tdual solutions. For the full Tdual solution means what is the NS sector and what is the RS sector. And I gave one example, the ADS5 S5 case. So now I just briefly mention what is Penrose limit. Just 1 minute. Okay. So now Penrose limit is actually for to every spacetime matrix or line element, means in every spacetime we have a metric or line element. And first we'll choose a null geodesic, and we're limiting the background around the null geodesics. Means we start a background in a generic background, means we have a metric and or line element. Now first consider the null geodesics, means the background admits some null geodesic, and then expand the background metric around the null geodesics. Means we are actually zooming the background metric around the null geodesics. Okay. So first consider the geodesic equation. So this is my geodesic equation. Now consider a particle is moving along some isometric direction, let's say x, and okay. So now this, and there is no acceleration and nothing all in other direction. So we'll actually end up with this expression. And if you break down this expression, you will end up with this one. So this one is actually we will take care when you talk about the geodesic condition. However, we also impose the null geodesic condition because the particle is moving with very high speed. So means it follows the null geodesic. So apart from ensure this expression, we have to make sure that d square equal to 0, which is the null geodesic condition. Okay. So now I am entering the core part of our work. Anyway, so now as we know, in 1997, the Johan Maldacena introduced his famous ADS-CFT duality with the background for ADS5S5 with the correspondence with the n equal to 4 superangles theory. Now, after Maldacena in 1997, after Maldacena introduced this ADS5S5 n equal to 4 superangles duality, the other people started looking what are the gravity duals for the 4-dimensional CFTs. And the next work is carried out by Klebanov and Tseytlin in 1999. So they considered the ND3 branes and placed in the conical singularity. And there, this dual background is actually known as the ADS5 T11, and T11 metric is written here. So this is the work by the Klebanov and Tseytlin in 1999, and this was the T11 metric. However, you can see from T1, so T1, okay, so this is the T11 metric. And you can see the topologically T11 is actually S2 times ST some vibration. So now apart from the regular D3 regular brane, so as it admits, yes. Okay. So apart from the regular, so as the T11 admits some more cycles, so apart from regular branes, so one can consider the wrap brane, or the which is actually the fractional brane. So brane can wrap also with the cycles. So this actually work carried out by the Klebanov-Tseytlin in 2000. So they consider, apart from n regular D3 branes, they consider the m fractional D3 branes, which is actually the wrap B5 branes, or the wrapping with the cycles. And they end up with and they end up with some n equal to 1 supersymmetric gas theory with SU n plus m times SU n, where n is very large. However, this theory is no longer conformal due to the presence of the fractional D3 brane or wrap B5 brane. Okay, and the geometry of this background is given by this expression, and this the HR is a wrap factor over the Minkowski space as well as the transverse Calabi-Yau space. So this is the wrap factor, and this wrap factor is contained by a logarithmic factor. Okay, so now due to the presence of the fractional brane, there are some certain difference if you compare the Klebanov-Tseytlin background with from Klebanov-Witten background, and differences in the NS sector. This background actually contains some non-trivial Klebanov field given by this expression where TR is some wrap factor, and due to the presence of the fractional D3 branes, which is actually the D5 the wrap D5 brane, which creates actually F3 contribution to the cycles of T11, and this is actually the F3, and as you know is also we have a F5 contribution which comes from the regular D3 branes. So this is actually some volume, some up to subfactor with some volume of T1. Okay. Now one can consider the type 2B supergravity equation of motions and work out the corresponding the normalization factor, and these are the normalization factor for our case. Okay. Now it turns out that the P, which is actually the number of the fractional D3 branes, is the wrap defined branes in the original configurations. Okay. So now if we study the Killing algebra for the Klebanov-Tseytlin background, it turns out that it supports a SU2 isometry. Means your algebra actually the SU2 algebra. So means your background exhibits an SU2 isometry. Now Swansea people took care about this SU2 isometry, and Tdual is the Klebanov-Tseytlin background, and this is the solutions applying the non-abelian duality with respect to those SU2 isometry, and they end up with this background. However, this is a quite complicated background, but which I want to mention. You can see Kangun here also. The Minkowski part will remain as a Minkowski, and this one S2 will remain S2. One S2 will intact in the Tdual's case. However, the remaining part will change, and here actually we rephrase the H factor by introducing some notation at tilde to cover up the all constant factors. Okay.
So are they is this asymptotically ADS solution?
Asymptotically, no. There is a fractional brane. There is actually no ADS in original solution also.
Okay.
Because there is a fractional brane is there. There is along with D3, along with regular D3, we have also the fractional. So there is no ADS actually. Yeah. Okay. But in ADS5, S5 is quite fine.
Right.
Yeah. Okay. So now here actually is a quite complicated background. However, you have some symmetry. You can see from there is residual symmetry in the Tdual background. There is a S2 is there, and we have a U1 isometry which comes from the sigma 3 square. The sigma 3 is given by this expression. We have some residual isometry in Tdual background. So this background actually is supported by the 2 form and the dilaton in NS sector, and in RS sector we have all fluxes. All fluxes means we have a F0, F2, and F4. These all are there in our sector. Okay. And just as just as expressions, these are the 2 form in the NS sector. This is the 2 form in NS sector, and we have some S2, and over the other parts actually depends on the Lagrangian multiplier. So this is the B2 in my Tdual sector, and this is the Tdual dilator. Okay. So now in our sector, as I mentioned, the all flux is there. So this is my F0, and this is the F2 and F4. It's quite complicated background. However, this background is actually this background is actually a solution for the massive type 2A supergravity. Now, because where the F0 is kind of related to the Roman mass. Now, interestingly, unlike for the IDS5S5 case, this background solves the type 2A supergravity equation, as well as it preserves the supersymmetry for original compactification. So as we know, the Klebanov-Tseytlin or Klebanov-Witten background is n equal to 1 supersymmetric. It carries 8 supercharges. However, it turns out that in Tdual sector, it preserves the supersymmetry because the dualized direction doesn't depend on the killing spinner directions. Okay. So it's fine up to now this point. Okay. So yeah. Okay. So now we can see if we examine the Tdual background, means Tdual geometry, it turns out that we have a 2 isometric direction. One is the psi and one is phi 1. So then what in our work, we consider the motion of a particle with very high speed along these 2 isometric directions. So first took out the psi direction, and this is the component of the psi direction. And similarly, this one the metric component for the phi 1 directions. Okay, so first consider the psi direction. If you impose the null geodesic condition, means delta mu g psi equal to 0, you will end up with certain values of R and V2, which is R equal to R tilde and V2 equal to V0. But unfortunately, these are the singular values. Singular values means for these values, the background, the component G psi component itself vanishes. So one can't proceed along this direction. So we left the psi 1 direction completely and consider the phi 1 direction. And again, recalling the geodesic condition, we end up these values are allowed. Apart from all other G's, apart from other values, these are the singular values. Apart from these 3, all are the singular values. However, as I mentioned, apart from the condition G del mu G psi equal to 0, which is a geodesic condition, we have to also ensure the null geodesic condition in order to examine the PPY or the plane wave. Now, what we did in our work, first we consider some fixed R equal to R, we fix some R equal to constant, which is not R tilde or 0, some other constant, because these are the singular values. And we expand the background metric around the mean cos xi equal to 0, where xi is the mean cos coordinate, and R some constant, and these values we got by imposing the geodesic condition. However, it turns out that this expansion doesn't lead to a PPY of geometry. Now it's obvious, because the Blau's theorem states that expansion around the null geodesic will end up with a PPY metric, that's fine, but it doesn't mean that all null geodesic will give rise to the PPY of geometry. Okay, so we leave these directions. Now, what we consider a motion of a particle. We consider the motion of a particle with non-zero angular momentum. Means we consider, instead of going some one direction, we consider motion in a plane. And the plane what we fixed is R phi 1. Now immediately one can ask, why not you consider the I psi direction, where psi direction is trivial. Trivial in the sense we can't even proceed about psi direction. Rather, as we got some non-trivial contribution comes from the phi 1, so we consider the motion in R phi 1 directions. And we expand around the xi is equal to 0, the mean cos is equal to 0, and the expression we got by imposing geodesic condition. So we propose the expansion as follows. And with this one, and we subsequently take the L tends to infinity limit. Now we have to fix the coefficients where is written here. So first we impose the null geodesic condition. This null geodesic condition actually fixes this out of 6 coefficient. This null geodesic condition fixes the 3 coefficient. And now after expansion, it turns out that we have some diverging term, which is order of L. Now in order to remove the divergence terms, it turns out that this C3 and C5 is actually not independent. They are actually related by this expression. So at the end of the day, So at the end of the day, is only one unknown, is either C3 or C5. Okay.
The W is also null coordinate.
Sorry?
The W.
Yes.
Is the null coordinate?
Yeah.
Okay.
It's just some,
so
yeah,
U
some.
and V and W.
UV has some UAV is as usual the light cone coordinates.
Okay.
And W is actually written. Okay, sorry. W is actually some scale coordinate. Some U in terms of V2 and V3.
Okay.
Yeah. Okay. Thanks. Okay. So now people use some usual normalize in order to normalize the du dv term. Some usual normalization for the 2 du dv term. We got the C6 metric. Okay. We got the C6 coefficient. Okay. So now after the expansion, we end up this metric, and metric is smooth because there is no order of L and order of L square term. And this is the metric after the expansion around the null geodesics. However, there is still one is missing to work out either C3 or C5. That we will take care later. Okay. So now this metric is actually supported by B2 and phi in NS sector and F2 and F4 in our sector. So F0 is actually goes to 0. The massive part goes to 0 if you consider the Penrose limit. Okay. So now this metric is actually not in the Bigman form. However, we know in order to take care of the PPA metric, it is easy to consider the Bigman gauge or Bigman representation for some certain advantages. So our next job was to bring down this metric in the Bigman form. In order to do that, okay. So this was a metric what we talk about. This is not in the Bigman form. So in order to express in the Bigman form, we consider a diffeomorphism in the transverse direction as well as in one light cone coordinates, one light cone direction given by this expression, and then this one is the Bigman metric. And you can see if you consider the wavefronts, means U equal to constant, this wavefront is actually the plane wavefront, which is given by the metric some Ri. Okay. So now for our case, this is the Bigman form where Fi can be worked out from these expressions. However, so this is a metric in the Bigman form, so we have to also express the background fields in the Bigman forms. Okay. So now this is the background fields. This is the dilaton in it. So this is the NS sector, means this is the dilaton in the PPF limit, and this is actually the NS from flux in PPF limit in terms of the Bigman representation. However, you can see that the H3 has a leg along U direction, so it is a null flux, and it is indeed true because we know from the Blau construction that the PPF limit, all the matter fields or all the fluxes is actually the null fluxes, means any flux, like any p-form flux you have, so Fp square equal to 0. Okay. And that was the NS sector, and this is the RS sector. RS sector, as I just said, the F0 goes to 0, but we have a contribution from F2 and F4, and these are the background fields for the RS sector at PPF limit in terms of the Bigman representation. Here also you can see this all the fluxes, means F2 and F4 has a leg along U direction. This ensures that these are the null fluxes. Okay. So now means these backgrounds satisfy whatever we have checked in our paper. The background satisfied the type 2A supergravity equation of motions and satisfy the Bianchi identity. So indeed, it is solutions of type 2A supergravity. However, there is still one missing about the C3 and C5, which we order to fix now. Okay. So in order to fix either C3 and C5, we borrow the idea, we actually took help from the Einstein equation for the type 2A supergravity. And this is actually the equation of the type 2A. This is the Einstein equation. There are two equations for the type 2A supergravity. However, second one equation is actually trivially true for the PPF geometry, because we know the for the PPF geometry, the all curvature scalar that I mentioned at the very beginning, that's all curvature is actually all curvature invariance goes to 0. So R equal to 0 for the PPF case. And as I mentioned, just is all of the null fluxes, so H square equal to 0. And we check separately in our solution, we check separately these two terms, and this way separately 0. So this is actually trivially 2. We didn't get any non-trivial contribution to fix C5, we didn't get any non-trivial contribution from the second one. However, for the first equation, as we know from the Bigman representation, and that is the advantage to express the PP wave in the Bigman form, because if you consider the PP wave in the Bigman form, only non-zero contribution of R mu nu comes from the RUU. And if you consider the expression of the RUU, and okay, so this only non-zero contribution comes from the RUU. So that actually helps a lot in order to fix the C3 or C5. Okay. So this is actually the component. This is the Einstein equation for the RUU part. And we know if you express the PP wave in the Bigman form, which is actually the du square, actually if a du square term is give you the RUU. Now, if you work out the HU square in our PP wave case, this HU square actually involved with C5. So in order to fix the C5, we'll take the Einstein equation, and this expression is actually solved. This equation is actually fixed the C5. So this actually end the gravity side of my work. So yeah, so this is my end of the gravity side of my work. So now I will talk about some field theory part. Okay, so Kangun, how much time I have?
You have 50 minutes.
Oh, great. Okay. So, so now this actually end my gravity part. So now actually I make some comments about the field theory part, but it is not actually well understood. Not about this case, the non-Abelian T-dual geometry has some issues in order to understand the T-dual, for the dual gas theory for the T-dual configuration. However, as I mentioned, the field theory dual for the original type 2B solutions is actually the non-conformal n equal to supersymmetric background with any SU n plus m times SU n gas theory for large Nm. And this actually describes the dynamics of n regular D3 branes and m fractional D3 branes, which is actually the RAP D5 branes placed near a conical singularity. Now there is actually some constructions are there in order to understand dual field theory. And this construction is actually worked out by this Swansea people very recently. So in order to understand the dual field theory for the non-Abelian T-dual case, first the main actually understanding is the domain wall formulation. Means how one can construct the domain wall for the T-dual case. And it is compared the domain wall with the original solution. So now for original Klebanov-Tseytlin case, one can form a domain wall by consider a D5 brane and extend it along some R12 direction, which is actually some part of the Minkowski directions, and wrap, and one can consider, and this D5 plane is actually wrap the compact, that's why we call the wrap plane, and this actually wrap the dualized directions, means the theta 1, theta 2, phi, theta 2, phi 2, and psi, which is actually we consider for the dualization. Now, one can consider the low energy excitations. One can consider the bond in field actions with the wall volume of this D5 brane, and this end up with some effective tension. Now, this people is actually carried out the same analysis for the T-dual case. However, instead of D5, okay, so here first we perform the non-Abelian duality with this SU2 isometry parameterized by theta 2, phi 2, and psi. And this actually becomes the RAP D5 branes, is actually gives rise to some D2 brane and extending along R12 direction of the dualized geometry. Now, along the same line, one can consider the wall volume of the bond in field actions for the wall volume of D2 brane, and we end up with some effective tension. However, it turns out that these effective tensions, because before dualization and after dualization, is actually matched up to a constant factor. So it actually doesn't give some new information because it's along the same line. Okay, so now one can consider the holographic central charge. One can work out the holographic central charge by Rui-Takanagi formulations. And it turns out that this is actually RG independent. So this actually turns out these two descriptions. One is the bond in field actions and the holographic central charge calculation it doesn't give any new insights. Means there is along the same line for the original solution as well as in Tdual solution. However, we can consider the gauge coupling analysis, and if you see their work, so this turns out that the gauge coupling behavior is quite mysterious behavior in the Tdual theory. It goes to some log R3/2, which is actually quite different from usual field theory. So means the dual field theory is maybe some high dimensional field theory, or dual field theory can't actually is completely different from the conventional field theory what we talk about. Okay, so now actually one can calculate the brane charge for the original as well as the Tdual background. So in original geometry, as I mentioned, we have a D3 regular D3 brane and the wrap D5 brane. So one can calculate their charges, means the Maxwell and Page charges, and these are given by this expression. So these are the Maxwell charge for the two branes and followed by the Page charge of same branes. Okay, here I'm just introduce some Q notation, which is some K plus PTR. Now, as I just mentioned, in dual geometry, we have a contribution from F0, F2, and F4. So this indicates that in dual sector, we have a D6 and D8 brane. And this D6 actually and if you calculate their charges, means the Maxwell as well as Page charge. So in dual geometry, this is the charges of the brane. Okay, now if you compare their dual charge with the original charge, it turns out that actually D5 branes goes to D8 brane, and each D6 brane actually matched, so twice the number of D6 brane is actually matched with the D3 brane charge. So we can naively say that after T-duality, D5 goes to D8, sorry, D5 goes to D8 and D3 goes to D6. So this is actually somehow, if you compare, so this is in T-duality, this is actually understanding that if you compare the brane charges for the original and the T-dual sector, you can think about how the dual field theory can inhibit from the brane construction. Okay. So, Kangan, so this is actually what you were talking about the deep brane and all these issues in the T-dual sector. Yeah. So now, actually, now the Swansea people, what they consider, they actually observe there is some Seiberg duality presence in the T-dual picture also. You know, for the original ADS5, for the original Klebanov-Tseytlin background, we have a Seiberg duality. Seiberg duality means, in the geometric sense of the Seiberg duality, means if you consider the D3 brane Page charge, and if you introduce a large gauge transformations on the B2, so it induces some charge in the D3, means the D3 brane charge will get changed. The same change can be observed in the Maxwell charge for the D5 brane by suitable change of the radial coordinate. This is actually some geometric reflection of the Seiberg duality in original compactifications. However, the Swansea people has observed the same Seiberg duality geometrically. Seiberg duality presents in the T-dual sector, but here instead of D3, the role plays by the D6 brane. So means,
I have a very basic question. Sorry.
Yeah.
So
Yeah.
usual abelian T-duality, if you take the T-duality transformation, then it goes to, so for example, if we take a T-duality transformation of dp brane, then it goes to dp plus 1 or dp minus 1 direction of the T-duality. So if we take the non-abelian T-duality, then it becomes a d plus n or whatever. The direction
Yes.
Or
No. You can see. So these are actually these are all like open directions about the non-abelian T-duality. So as you told, for the abelian case is actually simply to understand how the brane charge. Because if you consider what is abelian T-duality, naively R goes to alpha prime by R. So it's one circle, this big circle to small circle. So you just shrink that one circle, means when you just shrinking one directions and one other direction will sans. So means and along the direction, what you are saying that brane will get changed like P2, P plus 1. But you know, this non-abelian duality is actually open up a completely non-compact directions. So only way to examine what are the branes configuration can have in the configuration, if you examine the fluxes in the Tdual sector and how their charge behaves. Otherwise, you can't visualize from like its abelian counterpart. You can't visualize like, because there is no like big circle to small circles or one direction sinks, one direction sunks, nothing is like that.
Sorry, so the T-dual T directions, the isometric direction is the orthogonal to the branes or in this setup?
Yeah, yeah.
Okay.
Yeah.
So is this somewhat different with the abelian case?
Yeah, yeah.
Okay.
It's actually, you can see then, it's actually, although it's, people talk about this is non-abelian T-duality, but it's actually quite different. At the very beginning, it looks same, but in field theory perspective or in brain structure is actually completely different from its abelian counterpart. You can't actually you can't compare with its abelian counterpart actually.
So is there any known some dictionary or rules for how to map to the?
No, you can't. So far, there is no general dictionary. You have to consider by solution actually.
Okay, okay.
So I am actually sorry to say this only available is ADS5S5, the Klebanov-Tseytlin one. Even for this case, what I am talking about, if you consider for the Klebanov-Tseytlin case, the brain structure in non-abelian T-duality, in non-abelian T-dual background, the brain structure is quite understandable. Quite understandable means how the brain wrap or how the intersecting brain, all these things are quite understandable. And very recently, in 2007 end, by these people actually, there is a JF paper. Anyway, but in this case, when itself, the Klebanov-Tseytlin background, how the dual theory behaves, means what is the QR in the dual theory, that is also not quite understandable. And we don't know actually what is the QR and how the gauge groups are increasing or decreasing, or what is the what is the QR, we don't know so far.
Thank you.
Yeah, so these are all like open directions. Okay. Okay. So just I mentioned that instead of in dual sector, we observed, the people have observed there are some cyber duality, but in terms of D6 brain, as like D3 plates in original solution. And you can see by considering the calculation of the brain charge, that D6 brain charge is actually twice the D3 brain charge. So means the only understanding is the Q varies if you just if the M amount of charge induced in the D3 brain by considering the cyber duality for the original solution is corresponding the 2M charge, actually the 2M charge induced in the D6 brain in the Tdual sector. However, if you consider, if you calculate the brain charge at the PPF limit, it turns out that they all vanishes. So there is no cascading picture is present in at PPF limit. Means the PPF limit is actually the end point. So there is a fixed point, and there is RG flow along the cuber, and there is in the PPF geometry is only our understanding is this. The PPF geometry is actually the end point at the cuber. So there is nothing more actually. So there is no more cascading. Okay. Okay. So now at the very end. So just as a wrapping up, not wrapping brain, wrapping my talk. So we studied the Non-Abelian T-dual solutions originate from the Klebanov-Tseytlin background. And as I mentioned, and also Kangun was asking, there are so many like open direction about the non-abelian duality, but so far understanding is it provides some new supergravity solution, is interesting as far as the classical level is concerned. And we consider some very null geodesic and obtain the Penrose limit in the non-abelian background. And so we end up with a PPF geometry for this Penrose limit that we consider for the PPF which carries actually angular momentum. And just I mentioned our understanding is at the PPF limit, there is no cascading because the PPF actually sits at the ends points of the cuber. So means there is nothing more cascading. However, there is some missing. There are so many things are missing. Means we couldn't identify the proper BMN sector even because the dual cuber itself is not available. So we couldn't identify the BMN sector, and as I told at very beginning, there is a one-to-one correspondence between the closing modes to this set of operators, which is actually the BMN operators. But anyway, actually we couldn't highlight, we couldn't get this BMN sector in our work, And there is also need a precise mapping, means there is a one-to-one correspondence between the this holographic computed quantities, means the string like the sting modes for the closed sting modes and the field theory observables. Okay. So as a future directions, now there is actually too many directions are there, because this non-compactness also is a serious issue. But however, we are now actually exploring the PP wave in the full Klebanov-Tseytlin background, as well as some coset geometry. And interestingly, we have also some deformed supergravity background, because the lambda eta deformed background, as well as in the background with various C factors. So now in our present work, me and Prashanta is actually involved to trying to get some PP wave geometry in some lambda deformed background. And our actually what we want, that we are trying to explore that first, is there any PP wave geometry admits or not in the lambda deformed background, and at PP wave limit still there is dependence in any metric or any background field. It still depends on some lambda parameter or not. Okay. So these are some key references of my work. And okay, yeah, so these are the key references of my work. Main is these two are references. Okay. And okay, I'll stop here, and thanks for the attention.
Thank you for a nice talk.
Yeah,
yeah. Is there any question? I have some basic question about So usually after taking the non-Abelian T-dual transformation, the isometry is still preserved or usually broken?
Sorry, Kangan, I didn't get. Can you repeat once more?
So if you start from, for example, SU2 isometry,
yes,
and then you take a T-dual transformation, then still the SU2 symmetry preserved, or
no, it will broken. It will broken.
Okay.
Yeah, so it will broken, and that is actually that is also I should mention. So in abelian case, if you start with like any U1 isometry, you will end up with a U1 isometry.
Yeah.
So you can like you can go like to and fro direction. So one to another, again you can go back. But in non-Abelian T-duality, you can't even go back to your original solution. But what I should mention, as you asked, there are some remedy to go back. Means then you have to talk about the Poissonly T-duality. And it turns out that there is actually two main issues. One is what you have just asked about the, like, can I just restore the symmetry or not? And then another one is the non-compactation. So restoring the symmetry, in non-Abelian T-duality, you just loses the symmetry. But you can, if you consider some Poissonly T-duality, where it can be shown that, it can be, it will come. So it can be shown that non-Abelian T-duality is a subset of Poissonly T-duality. But if you consider the Poissonly T-duality, and if you have some certain Poissonly structure, from that sense, you can see that in dual sector, you have still some, you will have the symmetry also. But it is, but it is actually the Poissonly structure, and what actually I'm not quite actually fine with, means I'm quite not understandable about the structure. I'm trying to actually understand the Poissonly structure.
Okay, so is it possible to, I mean, I don't know whether it is a correct question or not, but can you do the Poissonly T-duality transformation rather than non-Abelian T-duality if it is more general? Then but yeah, thanks for your question, but I am not so far actually I am not quite understand the Poissonly T-duality, so I can't at this. Sorry, actually, I'm at this present. This present I can't give you answer, but surely I hope I will get back you within some 2-3 months or so. Yeah. I hope so.
Yeah.
And I'd like to ask you that. This PP wave limit and non-Abelian T-duality.
Yeah.
Are they commute? So you start from the after the T-duality?
No. It doesn't commute. It doesn't commute.
Okay.
It doesn't commute.
So
not only that, you can't actually, if you want to examine the PPA in original configuration. That's actually a nice question. So if you consider the PPA for original configuration and PPA for the Tdual sector. And now your question is, can I just go one to another and no, right. Certainly not. Because first of all, you just your chirality of the theory has got changed. Let's say you start with forget about all these things. Let's start with some ADS5 S5 background, which is the type 2A compactification. And we end up with, and if you do to the non-abelian duality, you end up with some type 2A configuration. And you actually background fields are completely different because you have RS sector, you have also contribution. So so you can't like jump from one to another. And as you asked, you should mention another thing about the chirality. So it turns out that for the non-abelian T-duality, if your group is even means if you number of generators. So if your group is like even, you will end up with same chirality. And if your group is odd, then you will end up with opposite chirality. As like for the ADS5 S5, we dualize about the SU2. And SU2 means we have 3 generators. So you end up with actually type 2A solution because the chirality has get changed. But if you see the construction about the coset, like SO4 modulo by SO3 or so, you will end up with same chirality theory.
Okay. Is there any more question?
Sorry?
I'm asking more question. Okay. If not, let's thanks to Sourav again.
Thanks, Kangun, again to give me the opportunity to talk here, and I will